Hello everyone, welcome to a new chapter where we delve into this thing called complex numbers. So all our life we've been learning about real numbers. 1, 2, pi, negative half, all these are considered real numbers. But now we're going to look at complex numbers. So before we start on complex numbers, I want you to think of something. Remember when your teacher told you you cannot take the square root of a negative number? Right. In this case, I want to define I, the imaginary unit, as the square root of negative 1. So actually what I get is that I squared equals to negative 1. Okay, what does this do? This imaginary unit I is actually the basis from which we build complex numbers upon. The first form of a complex number we're going to learn is the Cartesian form. So complex numbers, which we use z in this case to express a complex number, it will be equals to x plus yi, where if you look at this, x is just the real part, and the imaginary part will just be y. So for example, if we have a complex number, z equals to 2 plus 3i, your real part will just be 2, and your imaginary part will just be 3. Let's give another example. Let's say we have negative 3 minus 4i. Then the real part will be negative 3, and the imaginary part will be negative 4. But note, we can also have the real part and imaginary part be 0, because x and y are just real numbers. So for example, if we have the real part as equals to 0, then we have z equals to yi. For example, we can have z equals to 2i, and that would just be a purely imaginary number, because there's only an imaginary part. And we can also have the imaginary part to be equals to 0. So we can have z equals to 3. And if you realize, this also means that real numbers are just a subset of complex numbers, which is really interesting. So again, let's look back at the real number line. We've been using this all our life, this one-dimensional line, to express a set of real numbers. For example, 0, 1, 1.5, negative pi, we can all put this on a real number line, on one axis. But now what we're going to learn is this thing called an Argand diagram, which is kind of like a two-dimensional graph sort of thing with a horizontal and a vertical axis. This is not the same as a graph, because your horizontal axis will be the real part of the complex number, and your vertical axis will just be the imaginary part of the complex number. So let's see how to plot something, such as 2 plus I. If we have 2 plus I, we'll plot a 2 on the real axis and a 1 on the imaginary axis. And this will get us 2 plus I, which we represent by either a dot over here or a little arrow, which we can recognize as a vector. We'll talk about using complex numbers as sort of like vectors a bit later in the future. But for now, let's look at negative 3 minus 2i, where we have negative 3, the real part, on the horizontal axis, and negative 2, which is the imaginary part, on the vertical axis. And that's our point over here, negative 3 minus 2i. So again, we can think of complex numbers kind of like two-dimensional numbers. Now let's take a look at the 4 operations. How are we going to use addition, subtraction, multiplication, and division for complex numbers? Okay, let me zoom into it a little bit. Let's say we want to do addition and subtraction first. So addition and subtraction is quite simple. What we're going to do is just add up the real parts, which in this case is 2 plus 4, and this will simply give us 6. And then we'll add up the imaginary parts, which is 3i minus 2i. And this will net us I. So we get 6 plus I. Okay, simple enough. Let's do multiplication. So for multiplication, we can treat this such as a rainbow expansion. We get 2 times 4, which will simply give us 8. And then, let's do 2 times negative 2i, which will net us minus 4i. Again, let's do 3i times 4, which is just plus 12i. And the final part, where we have 3i times negative 2i. So let's look at this for a bit. This will give us negative 6 I squared. And again, remember I squared equals to negative 1. So we get negative 6 times negative 1, which is just plus 6. So we just get plus 6. And if we simplify this, again, we just add up the real parts, 14, and then we add up the imaginary parts, we'll get plus 8i, and that's our final answer. The next one is division, which will perform sort of like a conjugation. So remember, let's say we have 2 plus square root 2 over 3 minus square root 2. We'll actually take the conjugate at the bottom and times this by 3 plus root 2, and times the numerator by the same 3 plus root 2. Am I right? So similarly, we'll multiply this by the conjugate, 3 plus I. And here, we multiply this by 3 plus I too. Again, later we'll learn a little bit more in depth into complex conjugates. So what we do over here, at the bottom we have a difference of two squares, 9 minus I squared, which is just 9 plus 1, or 10. And over here we have the multiplication of 2 plus I and 3 plus I, which will give us 6 plus 2i plus 3i, which is plus 5i, and we get plus I squared, which plus I squared is just minus 1. So if we simplify this, we actually just get half plus half I. And that's it. We have done our division. We can actually use the GDC to help us do the 4 operations. So let's try this question from earlier. Go into the calculator and it will type 2 plus I over 3 minus I. So we'll key in the fraction and we have 2 plus I, and make sure to input the I from this pi button over here. We cannot just type the I in your keyboard. And then we have 3 minus, again, we input the I from this button over here and press enter. And we get our answer, half plus half I. While we're on the topic of conjugates, let's learn a little bit more about it. So if you have z equals to x plus yi, what I represent as the conjugate is just z star. And remember what we did? We had 3 plus I as the conjugate to 3 minus I. So in this case, we're just flipping the sign of the imaginary part. We have x minus yi as our complex conjugate. And if we look at this on an Argand diagram, you will see that your complex number, z, will just be over here. And your z star, which is your complex conjugate, will just be the reflection on the real axis. The next part we'll be delving a little bit into is the equality of complex numbers. So what is this property? If we have x plus yi equals to a plus bi, this just means that x equals to a. We are just comparing the real parts and we're equating them together. And again, the imaginary parts, y and b, will also be equated together. So again, to reiterate, the real parts of the left and right hand side will be equal, and the imaginary parts on the left and right hand side will be also equal. Okay, to test us a little bit, let's do a question. Find a and b given that square of a plus bi equals to 5 plus 12i, where a and b are positive real numbers. Okay, so let's dive straight into this question. What I want to do is do the expansion over here. A square plus 2abi minus b square, because remember you have bi whole thing square, which is just b square I square or negative b square, which will be equals to 5 plus 12i. And comparing the real parts, you will get a square minus b square, which is equals to 5. For the imaginary parts, we get 2ab equals to 12, or also that a equals to 6 over b. So what we want to do is actually use this to set up our substitution, where we sub equation 2 into equation 1. So what we see over here is 6 over b square minus b square equals to 5. What I want to do is times b square to everything. So what I get is 36 minus b to the power 4 is 5b squared. And I can rearrange this into a nice quadratic equation. Okay, not really a quadratic equation, but a quadratic equation in terms of b squared. If we do our factorization, we'll do b squared minus 4 and then b squared plus 9. If we look over here, the minus 4 and plus 9 get us negative 36. And minus 4b squared and plus 9b squared together will give us plus 5b squared. Again, if you're not familiar with how this works, please revise on your quadratic equations. So again, we see that b is a positive real number. Okay, if we actually try to simplify b squared plus 9 equals to 0, you can kind of see that this will be an imaginary number. B squared will be equals to negative 9. B will just be your root of negative 9. And if you split the cert here, square root of negative 1 times the square root of 9, we will get 3 from this part and then I. Just remember one more thing, I forgot the plus minus. So you need a plus minus in front of all of these. But again, since b is a positive real number and this is an imaginary number, we cannot use b squared plus 9. So we can just assume that b squared minus 4 is equal to 0. And this simplified will just be b equals to plus minus 2. We want to reject the negative 2 because b is a positive real number. So we get b equals to 2. And if we sub b equals to 2 into equation 1, we will just get a squared minus 2 squared, which is 4, equals to 5. And this gets us a squared equals to 9. And if we want to simplify this, this means that a equals to plus minus 3. But again, a has to be a positive real number. So this means that a can only be equals to 3. So in this case, our complex number over here is 3 plus 2i. So here's the summary sheet for the introduction to complex numbers. Let's take a look and recap what we have learned. First of all, we have learned the Cartesian form, the first form for complex numbers. We have a real part and an imaginary part. And by the equality of complex numbers, we can say that the real part on the left and right hand side will be the same, and the imaginary part on the left and right hand side will be the same. We can use this property to solve questions like this. Next, for the 4 operations, we can do addition, subtraction, multiplication, and division. And specifically for division, we'll use the conjugate. The conjugate is when we flip the sign of the imaginary part. Alright, thank you so much for watching. I hope you have a firm foundation for the next few lessons that we're going to go through.